Hi, everyone. My name is Davit. I'm the founder of Activeloop, and I'm super excited to talk about PatentPT today. But maybe before I get started, just briefly intro about myself. Before starting a company, I was doing a PhD at Princeton University, dealing with really large-scale data sets in neuroscience domain, and that all inspired me to start a company, get into Y Combinator, raise a couple rounds of financing, and start working with early companies in machine learning space to help them to be more efficient in terms of their data management. And what we realized is that you have all these awesome databases, data warehouses, data lakes, lakehouses specialized for analytical workloads, but you don't have one for unstructured data, for deep learning data, and that's where Deep Lake has been born. Today, we're going to talk about very specialized use case about PatentPT and how to build large language model-based solution using enterprise-grade memory agents. I'll get into details in a bit, but I think what we have seen over the last 6 months is that all this boom of generative AI applications is that it's so easy to build a shiny demo, put it on Twitter, get it viral, but it's not equal to building a production-grade ready product. And one of the reasons is, like, if you look back into 5 years ago, it's very similar to, it's easy to put a self-driving car on a neighborhood and drive very slowly. But if you want to put it on a highway, you have to actually nail all the edge cases and nail down. It took us more than 5 years, maybe 7 or 8 years, to get this to the level that we can trust the models drive with autopilot. And the core understanding is, like, how can we build this data flywheel where you collect more data, you fine-tune or train your large language models or visual models, and then iterate. Then it's also super easy to build basically this very thin layers on top of the OpenAI, but the main mod that you get as a company is actually the data you collect and how this transfers into the learnings that the LLMs will get specialized for your use cases. Another problem is that this large language model input is limited. They have a limited context size. And that's where you have the need for having a vector database where they can store much larger set of data and only retrieve pieces of it into the context so that the LLM can reason about it. But actually, vector search is not solving retrieval problem. Information retrieval has been long-lasting area in computer science. And you actually need way more advanced types of queries to be able to operate on top of the data. And more or less, a lot of the storages don't really operate aside from embeddings. When you want to store images, video, audio, text along with your data for different purposes, this doesn't work out. So what we have seen from how the AI data stack has been evolving is that if you talk to a lot of companies, you have maybe a data warehouse or a database where you store the metadata. Maybe it should be in Postgres or Snowflake. You have a bunch of images storing on top of S3 that is in unstructured form. And then now you have to employ the third type of tooling, which you call a vector database, to be able to store the embeddings. And then now, if you start to iterate over this loop, you have to run a query in Snowflake, export the view, link the images, copy the data to the machine, start doing the pre-processing and then training, iterate multiple times, and then at the end get to the inference stage, run the inference, generate the embeddings, store them in a vector DB, then link back, this vector DB belongs to this image, and then you have to iterate all over this place. And it is becoming time-consuming for data scientists and super inefficient in terms of the data workflow, how these all operations are being done. And what at Activeloop we focus on is unifying these 3 different tools to create a storage layer that can directly stream the data from S3 to the pre-processing of the data of training or running inference. And both you can run queries for vector search applications or use it as a data lake for your deep learning application. And that's where our solution comes into the place, where on one side you can run search to run the queries which we build a query engine. I'll get into details in a bit. And from the other side, you have the streaming engine that can stream the data to your training or fine-tuning applications. And you have below it the deep lake that sits on top of your own S3 or Google Cloud Storage or Azure Blob Storage to make it as cost-efficient and scalable to store the data with compute and storage isolation. And if you look from the ML lifecycle perspective, you have version control, with deep lake visualization, running queries, materializing them, and then streaming. And then the rest of this is taken care by other ML ops tools, including the evaluation, the deployment within your LangChain or Llama index integrations, and or the annotations tool that you need to annotate the data and then start retraining those models. So before getting into the use case, I'll give you a quick intro on what deep lake technology runs behind the scenes. Is basically you have this compute and storage isolation that makes it very easy to separate. And what we do is that we take whenever you give us data, it could be a bunch of documents, could be images, could be JSON files as well. We group them together into so-called tiles or chunks. Sorry for misuse of the words of chunks, because within large language models, there's another context for chunking as well. But basically, since it's very inefficient to store file by file on top of S3, we group them together and put them into columns, which we call tensors. So you can have one column that's for images, you can have another column for embeddings, you can have another column for text. And then this layout structures the data so that we can run on top of that queries or stream them to your training or fine-tuning process. More than that, once you start ingesting the data, you actually keep you with version control. So you can start with an empty data set, add 100 images, or maybe they could be not the images themselves, maybe pointers to the images, check out to new branch, add annotations, maybe merge back, update few of those. And then now you have a commit. At any commit, you can run a query, create a view, and this view can be sent to the training process. So you have a full understanding of how your data lineage is growing over the time that gives a clarity on which model has been trained on which data. We built also from ground up a tensor query language, which think of it as an extension to SQL that not only can run queries on give me images that contain a bicycle during a rating period, but you can also apply transformations on top of the images, adjust the bounding boxes, and also order it by its a user-defined function. What this is really helpful is similar in self-driving case scenario. I don't know if you're following Elon Musk on having the autopilot driving him in Bay Area. That you will observe is that one of the key insights that they figured out is that, first of all, they removed all the manual or human engineering code from the autopilot FSD, fully self-driving car driving. But then the problem is that when they collected a lot of data, they found out that the humans, when they drive, they actually don't stop at the stop sign. So the average stop sign stopping point was 0.5 seconds. And the way for them to go and solve this, obviously, like one would say, hey, go and just add a written code that says if you see a stop sign, you should like wait for 3 seconds or 2 seconds. But actually, since they imply an end-to-end neural network decision-making framework, the solution to this problem is go and upsample the cases where drivers are actually stopping at the stop sign for more than a second. And then if you have that condition, then you can upsample the data, send this to the training process. So your large visual model or large language model can actually have good understanding of all the edge cases that your production or application workload is experiencing, and then use this then for production use cases. And then once you run the query, you know, okay, here's my data that I want to feed this into the training process. Then we have built a streaming engine that you can stream this data to your GPU compute to train your own large language models or visual models on your own cloud. But also you can send this to already ready APIs like OpenAI to fine-tune the model there as well. And the streaming data loaders that we build is like, think of it as like more Netflix for data sets, where the data can be streamed from the storage to the computing machines, saving all the time that you have to transfer the data all around, copy them, and store them. And at the same time, you can visualize data. You can have both quantitative and qualitative understanding of the data sets, both for tabular data, for vector embeddings, visualize the embeddings themselves. And more interestingly, you can also, when you run a query, you can see how the distribution of the data itself is changing after the queries. So in short, Activeloop is a database for AI. We provide it's serverless with compute and storage isolation. So you can have a very good memory efficiency when you're scaling your workloads. It's multimodal. It helps you to store embeddings, text, audio, images, and videos. And it's all in one, where you can stream the data, run queries, and then visualize them. we have been working with many Fortune 500 companies and also partners, collaborating on using Deep Lake and Activeloop in enterprise setting, and also a lot of startups and generative AI teams that are using Deep Lake as their storage for processing a lot of documents. So I think that was the kind of a brief intro about Activeloop and Deep Lake, and now we can actually get into the specific application to be having super excited working and collaborating with our partners, including Intel, AWS, and RC AI. So what's the problem? You have about 600,000 patents filed every year. And in total, you have about 80 million across the whole globe. The problem there is that it takes, in average, 2 to 4 weeks to generate these patents. And it's attorney work, it's the team's work. And if you even want to go and do a search on USPT website, you have this old school style keyword search or specifying, hey, here's what I'm looking for, this is what I need. And then you get a list of documents, you have to go and manually review them. And then if you want to generate one, you have to read and try to generate one. So this is like the old school way of doing search, especially with systems that contain a lot of documents. And I think the solution here is like, hey, can we actually leverage large language models to solve this problem? And what we realized is that, first of all, there's not just one problem. It's not just the search problem. Maybe you want to generate abstracts. You want to generate claims. The patent has itself a structure. So what we created is this, what we call PatentPT. Think of it as an enterprise-grade memory agents that routing together to solve a specific task or a query that user specifies. So not only has the different agencies, but also it specialized. You have like models that has been fine-tuned on the data set to behave way better. If you get into more details, here's the following setup where you have, when a user provides a query, the meta agent decides which agents should use it. You have some agents that just do claim search. Some of them are doing abstract search, or some of them do generate model or fine-tune a model, or generate like instructions on how to access or have a question answering basically on the data that already is in the patents. And then the final answer is composed and then brought back to the user. So what we realized is that specializing each agent in a very well scoped, which means also like prompt engineering, making sure that the model they access is correct one, ends up with high fault tolerance and accuracy per execution. And then the meta agent itself is like becomes the orchestrator to make the decisions who should do what. So what we did is the following: is we first of all collected all the data, stored it in Activeloop Deep Lake. We collaborated with RCAI to fine-tune a model for both embeddings and also the LLM. Then with help from Intel and AWS to train and deploy this model. And of course, the data loader has been very critical there as well, because you could train and also run the queries on top of this data on the fly. So if we specialize in the last stage is like, hey, we have this data, we index the abstracts and claims, which are subsets of these patents. We create a featurizer that realizes that, hey, here's the data, how it should be indexed. This is what we used for a vector database Deep Lake to store the embeddings, and then connect to the framework with LangChain to run the queries, get the agency set up, and do that. But one of the key things that Deep Lake has specified is this ability of not only just doing similarity search, but taking the context and putting it into filtering the data. And these filters are automatically generated when you run a query. So let's say you run a query saying, hey, can you give me the patents from 2007? The query or the agent that's processing this query should realize that, hey, 2007 should not go part of the embedding because there's not any information there. It actually should be part of the filter where you can run like condition on all the documents that existed in 2007 and then bring back the vectors and then run embedding search on top of that. And this is like totally automated from the user specifying this manually, or the agent that has to do manual specification. So great. Let's do a demo quickly. So here, as you can see, a very basic, simple, think of it as a retrieval augmented generation task. You ask a question and you get an answer, what's happening behind the scenes. The meta agent decides that the question answering bot should go and run a query on Deep Lake, bring back the relevant patents, and then give it to the context, and then you can actually start answering these questions. Then what you can do here is that you say, I want to actually search for specific patents. You can see there's no any specific button that you say, hey, I'm switching from question answering to a search. And there's also no specific, in USPTO, you have seen that you have to go and manually say, hey, here's the date, etc. There's nothing there. And you can see that the different answer type is responded here, where Meta agent figured out the search use case with a specific year, and then it provided to the query engine to run this query and then bring back the results. But you can go further. You can say, hey, I want to actually generate patent abstracts or claims. So during in PatentPT use case, like you want to generate patents that are like they have an understanding, but they don't want to be the same, because then you will have plagiarism, or like basically your patent will not get accepted, saying here it is just a copy of another thing. What you can do instead, what we are doing here is like we run a query, get all the relevant claims, and we say, hey, you should generate something that's not doesn't exist before. So that's where the vector story is useful. And then what you can do on top of that, you can also take the output and then run a query, check, like similar to fact checking, but this is the inverse problem, is like you want to make sure that this claim doesn't exist before. And that's where the vector DB use case comes into the place. So I think it's kind of summarized the end-to-end use case where how to build enterprise-grade memory agents. I think the key critical thing is that if you are creating agency, then make sure that they are well scoped and they're solving specific domains. We showcase how Deep Lake can be used both from fine-tuning perspective of those models, and then also using them in production for your vector queries, or like vector queries that are with attributes. And there's way more things that we are, I'll share in a bit as well. We're super excited to mention this and have a sneak peek in a bit. Then you have like the architecture, how this gets deployed on the cloud with AWS and Intel products. And plus, obviously, all this gets together, like what you see, the fusion between compute, which is the large language models, and the memory, which is like Deep Lake in this case. So if you look from the different perspective, you have this stack. Think of this as your chip, like L1 cache, L2 cache, L3 cache, and then you have the RAM and the SSD. In our case here, you have a smaller context, large language model. You have a larger context, large language model. You have this memory API layer, which is the long chains, llama index, and the agents that operate on top of the vector databases, and they sit on top of data lake, which is used in return to train or fine-tune your large language models. So that's where Activeloop is actively, without pun there, solving the problems for data management for generative AI applications. And what we have realized is that, as I mentioned earlier in this talk, it's super excited to share this, is that vector search doesn't actually really solve the information retrieval problem. That's why you have to combine this with other solutions like lexical search that Elastic has been doing for the last decade. You have to maybe do this hybrid search, which is combining these different approaches, or do re-ranking on top of that, so that you end up with some complicated retrieval augmented generation task that solves the problem. However, like I think one of the key things that we realized is that based on type of queries, we can learn how to do better question answering without actually changing the vector search operation itself, with better indexing. So you can see here, if we take this evaluation data set, see what is the like for those who are not aware of, so maybe just give you a quick review of what this graph means. Is that on the x-axis you have recall, which think of this as the accuracy where you get top 10, let's say when you run a Google search, the recall one is responsible if the first link is the right link or not. If you run a search on Google search and then at least one of the right ones is at top 10, then this is considered as one. And then here you have the probability of like this validation set of how many of the questions that have been inside the recall one, inside 3, inside top 5, inside top 10, etc. And you can see if you do an Elasticsearch, this is like, or using their BM25 lexical search, think of it as a keyword search in very high level terms, then you can get the following accuracy at each level. What you care from the generative AI application is that the top K, which is like 10, in this case, is as high as possible, because if you don't provide the right context for your large language model, then it's going to hallucinate, right? So at least the vector DB or any information retrieval task beforehand should actually bring the highest level information. And then you can use any vector database here, doesn't matter which one. Maybe you use approximate nearest neighborhood search, like all the indexes that they provide. This will discount the vector search algorithm by 1% or 2%, but at least you get performance and scalability. Or you can do a hybrid search, which like maybe adds 1% on top of vector search. That's what we have found out from our evaluation set. And we are introducing deep memory here, that without changing anything, so you still use the vector search, you can actually get up to 5 to 10% improvement on your recall. And this becomes super critical when your RAG solutions, they work 70% of the time, and you want to keep pushing this to above 80 or 90%. We have seen some cases with our customers that goes way behind 18% for recall 10 improvement. But the key thinking here is that, look, like you have to be very critical on what kind of information you feed into large language models. You have to make sure that the accuracy or the recall at 10 is like it's like, or the top K, whatever number you decide on what the context should be aware of is taken. And then you can later worry about, okay, we need to fine tune our large language model, or we can fine tune the embeddings, etc. So this all gets in between. But deep memory, without changing anything. So you can still add your hybrid search, you can still add the re-ranking, you can still go and do your feature engineering. So everything stays the same thing, will enable you to improve the accuracy out of the box. And it's still in private beta. Feel free to reach us out if you want to get an early access. And we are super, super excited to release the public API soon. And one last moment as well. If you haven't yet tried, we have a pretty famous course on learning how to use long-chain and vector databases and building real-world generative AI applications. Please go to learn.activeloop.ai. It's a free certification program that we are doing in collaboration with Towards AI and Intel. And this will like really go through practical projects that you can get hands-on, understanding how to build generative AI applications. Yeah, that's it. Thank you very much. And super excited. And let me know if you have any questions. Happy to answer them. And feel free to reach me out on Twitter or LinkedIn. And yeah, love to get your hands on Deep Lake and Deep Memory and see what you will build with it.